Okay, so the goal of these lectures is to talk about some recent results towards the MMP for foliations. So more precisely, I'm just going to say a few words about what I'm planning to talk about. Today, it will be mostly about introduction or motivations. So in particular, I would talk about singularities after, for foliations, of course, after McQuillan and a few others. Then tomorrow, I will start talking about MMP. So, and the first results I will talk about are related to things like bend and break, cone theorem, and so on. So, of course, I'll talk about it tomorrow. And this will be, I will mention again tomorrow, but will be after the work of Spicer. And then on Wednesday, I talk about MMP for foliation threefolds after the work of us. These are the new recent work. Okay, so this is the plan. Now, I was told that I shouldn't assume too much about MMP. So let me start with a very quick introduction to MMP, which is also a way for me to motivate why I like foliations. There are many, many reasons to like foliations, but I have my personal opinion, and so I will talk about it now. But first, let me say a few words about MMP. So the goal somehow is to divide varieties in boxes. We want to not classify, because that's too much, but we want to try to understand how we can divide varieties. So in case of curves, so let's suppose that X is a smooth projective variety. And for these lectures, I will always work with the complex numbers. So I will always denote by n the dimension of X. So for curves, let's say much has been done, but from a Brashian point of view, there is nothing that needs to be said. So let me consider the case of surfaces. Let's consider, I just want to give a very, very brief, and probably some of you already heard me telling this story about MMP. Let's consider the space of all the smooth projective surfaces. It's a set, sorry. Don't think of it as a moduli space or anything like that. It's just a set. Okay? And I want to construct a graph whose vertices are this object. So this graph will be a directed graph. In other words, we have an arrow for given two objects inside here. So we say that we denote by this symbol here, where x and y are two elements here, so given x, y here. We denote by this symbol the blow up of a point. Okay, so this way we create a very, very big graph, right? With many connected components, where each vertex is an algebraic surface, and of course there are different ways to go to the same object, and so on. And of course it's not as far by being connected. So there are many of these pictures, and so on. And also, you see that if you start from a point here, there are infinitely many ways to go up. there is no way to go up because it's way too wild. On the other hand, going down, you don't have too much of a choice. So let me say a few remarks about this graph. So the first one is that two surfaces, x and y, are in the same connected component. If and only if they're birational. What does it mean they're birational? In other words, there exists U1 open set of Zariski open set of X and U2 Zariski open set of Y. So this is open and this is open, such that these two quasi-projective varieties are isomorphic. So this is the definition of birational. Okay, you can find some, of course, non-trivial, otherwise. Okay, so we have a very good understanding of what it means to be inside the connected components. So for instance, if you take P2 will be one of these components. It will be somewhere here because there is no arrow starting from P2. And all these surfaces are called rational surfaces. They're smooth rational surfaces. Okay, because they're birational to P2. This is just a definition if you want. All right, so what else can be said? I don't want to talk too much about this, but what else can we say? You say, well, though there is no way to study what happens above any given point, we can see what happens below. So let me say the second remark. The second remark is that if Kx is F, if you don't know some of these words, please let me know. I suppose Kx is the first string class of, or maybe minus the first string class of X, but in other words, it's the first string class of omega 1x, the cotangent bundle. Each of us has a different way to define it. And F means that Kx times any curves, we're on a projective variety, so there are many, many curves. On any curve, the degree of this divisor, it's non-negative. Okay, so if Kx is an F, then X is an endpoint. What does it mean, endpoint? So there exists no non-trivial, well actually by definition it's by far non-trivial, so there exists no arrow from X to Y for any Y. Okay, in other words, it's a bit like P2. You cannot go anywhere else starting from P2. And same thing for, so P2 is also an endpoint. Although Kx is not an F, it's actually the opposite, but this is also an endpoint. You can go above P2, but you cannot go below P2, and so on. So what is the goal of the Minamoto program? The goal of the Minamoto program is to find endpoints. So the goal, it's very vague, of course, but the goal of the MMP is to find endpoints. And of course, there are two questions. The first one is, do they exist? Actually, three questions, but let me just summarize into two. And the second question is, how many are there? And I should say that although this question I've been asking only for surfaces, something similar makes sense perfectly also in higher dimension. This is more or less what we do in the minimal model program. We want to see if you can find something which is a good representative of this rational class, and at the same time we want to know how many of these objects there are. So the answer for surfaces is pretty easy. If you want a third question is, what do they look like? Okay, let me just say that in the case of surfaces, but the same thing is expected to be true in any dimension, we have two possible cases. There is a dichotomy. Two possible cases. Okay, let me first say that existence for surfaces, it's always guaranteed, even for threefold, actually. This one I will distinguish two possible cases. You see, why it's possible that they don't, maybe I should say, why this question makes sense? Well, the reason why it makes sense is because you could have an infinite sequence of errors without ever reaching endpoint. For case of surface, it's pretty straightforward to show that this is not a possibility. But the reason why this question makes sense is because this is a huge, huge graph. So it's very possible that there is no finite path below a vertex x. Okay, so it's not a trivial question. It's actually a very hard question in general. Okay, the first case is assume that there are no global sections of kx. Okay, first of all, I should say that this is a rational invariant. What does it mean? It means that if this is true for one vertex, it will be true for any vertex in the same connected component. Okay, so this property is a rational invariant property. Okay, again, remember we're talking about surfaces. So although the answer is the same for any variety. So then the answer is, as I say, one, it's always yes. There are always infinitely many. Endpoints. Let me give an example. If you're talking about rational surfaces, then there are two families of, two kind of endpoint. Then there is P2, we already mentioned that. This is an endpoint. And then there is a Hirzebruch surface, Fn, where this is the projectivization of O plus On, where n is different from 1 or minus 1. Otherwise, it's a blow up of a point in P2. And this always maps to P1, and the fiber, it's P1. I mean, it's a P1 bundle. Okay, so these are all the endpoints. Sorry, let me write it here. Endpoints. Okay, so what is the property? There are many, many properties, except for the fact they're always infinite. But you see, they always have lots and lots of rational curves. P2 has a lot of rational curves, all the lines. And the Hirzebruch surface also have a lot of rational curves. In particular, all the fibers, all these P1s are rational curves. This is not true for the opposite case. There are not too many rational curves, and we will hear about that a lot. Okay, so the second case is there exists M such that h0 of xm and kx is different from 0. And of course, this is also a rational property because it's the opposite of this. So if it's true for one, it will be true for all the elements in the same rational class. And the answer is there is always a unique endpoint. Let me call it x min, because it's the minimum model, so called minimum model. So what does it mean? It means that no matter what x is, you can have huge amount of points here, but at the end you're going to have only one endpoint here, which is as nice as you can imagine. So let's see some problems. So we answered these two questions for the case of surface. This is very, very old. I mean, this is from Castelnuovo and the school. But we answered these two questions, and let me say a few words. So the first property is that exactly the opposite of what is written there is true. Meaning that if it's an endpoint, then this must be, so not the opposite, sorry, the vice versa. This must be an F. Okay, so we have a characterization of these mirror models. But we can say a bit more. Actually, even better, this guy here is semi-ample. I'm going to explain what it means. And from now, I'm going to start talking about foliations. But let me remind you, what is the definition of semi-ample? So there are many, many ways to define semi-ample, but maybe the one that you heard before is that there exists a positive integer, let me call it q, such that qkx is base point free. The linear system is base point free. So this means that if we take the map associated to qkx, this is a proper map. Let me call it phi for simplicity. And what is the property about this phi? The property is that, sorry, this is everywhere it's mean. You need to assume kx is an F. The property about this map is that this power of the canonical divisor is the pullback of an ample. On Y, of course. On Z, sorry, of course. Okay, so what it means is that, let's forget about Q. Q does not play any role here. What it means is that K comes from Z. Okay, so it's a very strong characterization of this X. First of all, there is a proper map. Very few varieties emit a proper map. So this is already very interesting. Okay, let me say, this is the end of the picture for surfaces. Let me say a few words about in general. In general, we expect to have a similar picture. And many results are known. So we expect because we don't know everything. But something like a similar picture should hold in general. And at the moment, I'm not going to say anything. I'm just going to say many results have been proven. So for instance, in dimension 3, everything's okay. This is maybe to do more in many other people in the 70s or 80s. Many other results are known to be true, but there is one problem which is still very open, which is exactly this one. So, but in general, so many results hold, but this conjecture is still open. And this conjecture is called abundance. do we know that what is written there is always true? So the conjecture is that if this is an F, then it should be semi-ample. Okay, very, very briefly, let me remind you, Kx in F means it's an endpoint, so it's a minimum model. Okay? So we expect that if it is, if it is an F, then this property is always true. And again, it's a very strong property because it tells us a lot about the canonical divisor of X. Okay? And I should say that in dimension 4 or higher than 4, this is very much open. Okay, so let me talk about, in 2 minutes, Siu's approach of this conjecture. Although it's very natural, but okay, so again, this is just an approach. We don't have many evidence that it's going to work. But first of all, if Kx is an F, if Kx is semi-ample, then there exists a map. There exists some kind of fibration. Oh, sorry, I should have said that this is, we can assume this to be surjective and we connect the fibers. Okay, of course, Z by definition is the image of this map. So it's surjective, and then by taking time factorization, we can always take with connected fibers. Okay, so fibration means exactly the same. Proper morphism, which is surjective and connected fibers. Okay, and the fibration is phi. But, and we will see it, any fibration induce a foliation. I will define what a foliation is in 5 minutes, but let me just say what is the foliation. It's just more or less, it's not true, but it's almost the kernel of the tangent bundle map into the tangent, of the tangent map. Okay, so given any fibration, we can always define a foliation. That's a fact. It's not quite true, this is defined by this, but it's the saturation of this. Okay, so let's for a moment forget what the word foliation means, but maybe we can do the opposite. So the first step would be, given Kx and F, can we find a foliation? I should say that both these steps are very, very open, but still, it's good to play. So the first step, given Kx and F, can we find a suitable, whatever suitable means, foliation induced by Kx? This is the first question, or the first step of Siu's approach. And the second step, yep.
Step 1 again.
Okay, given Kx and F, can we find a suitable? I don't know what suitable means. I can talk about it, but it's not very clear what it means. Foliation induced by Kx. So what I'm doing here is exactly the opposite. I'm assuming the conjecture is true, and so we know that there is a foliation. But we don't know if the conjecture is true. So let's do the opposite. Okay, we first find the foliation, but then once we find the foliation, maybe let me call it F. Given F, can we show that it is algebraically integrable? What does it mean, algebraically integrable? It means that it's induced by a fibration. Okay, so they are very, very obvious steps, but still each of them deserves to be studied. Okay, so somehow this is one of the reasons why I'm particularly interested in foliations. I don't think that from a Brashian point of view they've been studied enough, so that's how I got interested in this business. Any questions so far? Okay, so now we can start. I'm going to talk about, this is the end of the introduction, I'm going to talk about foliation. So the goal is to first remind you what a foliation is, and then I will talk about how to define, how to see all the properties that we need in order to run MMP. So definition. Okay, just to remind you one more time, X is always, for a moment, let's assume, although I'm going to drop this very soon, maybe I should say that in order to, sorry, I should have said that before. In order to generalize the minimum of the program, what has been clear for a long time is that we need to work with singular varieties. So for foliation, it's the same thing. We need to work with singular foliations. But it will be clear very, very soon why for foliation this is even more obvious. But for a moment, let's suppose that X is a complex manifold. Again, soon I will drop this assumption and the definition of foliation is exactly the same. Okay, so a foliation F of rank P, or alternatively corank Q, which is equal to M minus P, is the following data. So it's a coherent subsheaf, which I'm going to call TF of TX. So of rank P, sorry, let me write it, sorry, I should have said here, rank P a rank P coherent subsheaf TF of Tx will satisfy the following property. And I'm going to explain why these two properties are important, but they're both very natural. So the first property is that it's closed under Lie bracket. What does it mean? It means that you can define a map from the second wedge of TF to the quotient Tx in TF, and this is given by B wedge W mapped to the Lie bracket. This is exactly like in differential geometry. VW, and this map is always 0. Why? Because I'm quotienting by TF. I want this Lie bracket to live inside TF. So if I take the quotient, this map is 0. Okay, so this is the first property. Close under the Lie bracket. And the second property will be clear one moment. Why it's very natural is that if you define the quotient of Tx with Tf, this is torsion free. Okay, so this is called the normal sheaf associated to the foliation. So what is a foliation? It's just a sub-sheaf of Tx, but it's not only important to remember what the sheaf is. You need to remember how this is inside this one, because different embedding can give different foliations, even if Tf is always the same. So it's not only Tf, it's really an embedding of Tf inside Tx. Okay. So I'm going to give very few easy properties. Okay, so first of all, we have a sequence. This is by definition. But since I'm going to use it all the time, let me write it first. And the single locus of F, by definition, is the locus where this guy here is not locally free at X. Okay, so it's a closed subvariety of X. So let me first say one thing. You cannot live, there is no way, like in Miyamoto program, you cannot work with complex manifolds. In the same way, for foliation, you cannot work with smooth foliations. It makes almost no sense. There are too few smooth foliations. So we need to work with singularities, but that's okay. We'll see that this is okay. So let me first, before I justify this definition, let me say a few words. What is the goal of the Miyamoto program? Or the goal of these 3 lectures? Well, is to give a partial answer to these questions. The first one is that assume that Kf is non-F. Oh, sorry, I didn't define what Kf is. Sorry, let me go back to the here. Notations. I'm going to define omega 1 of F, exactly what you imagine, is the dual of Tf. And then I'm going to define Kf as the first chain class of omega 1 over F. So the way to think about this is exactly the same way to think of Kx. Let me say that this is a way to do it because I can choose Tf to be equal to Tx, right? Every time I'm been talking, I can take the trivial foliation, which is the one given by Tx. And of course, I'm saying nothing. I'm just saying that Kf is equal to Kx. So the goal of the Miyamoto program is to try to understand what are the properties of Kf which resemble Kx. So the first property is the bend and break. So which says that if Kf times C is negative, what can we say about C? So if you know the bend and break due to Mori, then you know that you should have a rational curve. And that's exactly what we expect to be true. So does there exist a curve, a rational curve, through, let me just say, the general point of C? If you remember, at the very beginning I told you there are 2 different kinds of surfaces. Those that have a lot of rational curves and those that don't have it. So somehow here we are on the first side of this picture. Okay? So this is a question. I mean, at the moment I'm not claiming anything. The second question is, suppose that there are few of these curves. Let me be naive. Let me just say that, assume that there are some global section, exactly like before. So this is the second case, if you remember. So can we find x birational, x prime birational to x? Okay, again, when we don't expect to be a manifold. Actually, it's never going to be, almost never going to be a manifold, but it doesn't matter. Such that if f prime is the foliation induced on x prime, then kf prime is net. So this is the goal of the Minier model program. Can we find, after some kind of operations, which are the birational, exactly like in the Minier model program, these are contraction flips, can we find another variety on which f becomes minimal? In other words, kf prime is nef. Okay, so this is the goal of the Minier model program. Now, let me go back to the definition. So let me leave this here for a moment. Let me wait here. Okay. So, first of all, the property 2, it's always an easy property. So in other words, we can just take the saturation. If you take any coherent subshift, you take the saturation, then automatically this property will become true. So 2 is equivalent in requiring that Tf inside Tx is saturated. Okay, you can always take any coherent subshift, take the saturation, and this property will be true. Okay, so 2 almost it's a trivial property. And also, 2 implies that the single locus of f, this is basic algebraic geometry, has codimension at least 2. If you remember, this one is very similar to the fact of normal varieties have singularity in codimension greater than 2. And always, you can always take a normal, given any variety, you can take a normalization and force this property to be true. Okay? So for foliation, it's the same thing. You can always get rid of codimension 1 singularities by taking saturation. Okay? So we'll never talk about a singular curve inside surface and so on. Okay, the third property, which is the most important one, I talk about 2. What about 1? Well, let me remind you what Frobenius' theorem says. So 1 implies that, well, of course also 2, I mean, why do we care about 1? Why do we care about Lie bracket? Well, this is the reason. Okay, so given any x, which is not contained in a single locus of f, we can find U, open analytic neighborhood, sorry, and we can find a fibration, how should I call it, phi, sorry, I don't have much fantasy, phi, such that, okay, first of all, this Q here is exactly the same Q as before. It's equal to n minus p, where p is the rank of the foliation. Okay? And also, if you remember, just now I talked about foliation induced by a fibration. So here is exactly the same story. So if we take the cotangent bundle associated to F, we restrict it to U. This is nothing but the pullback of this guy here. Okay, so what is the picture? The picture is very simple. You have a point P, X, which is not singular. This is very important, because in the singular locus, different things can happen. And then you have some kind of fibration, analytic fibration. And this maps to CQ. The way you should think of it is that all these subvarieties have tangent bundle, which is isomorphic exactly to the tangent bundle of the foliation, which is TF. Okay, so you should think of this to be tangent of, these are what I call the leaves of F. Okay, so this property will be used pretty much all the time, so it's good to keep in mind. Any questions so far? Okay, let's continue. Sorry, today, for many of you, this will be very boring, but it's good to have a common language, I suppose. Okay, there is a dual point of view, and since I'm going to use it a lot of times, I think, let me talk about it for 1 minute. So instead of thinking of a subsheaf of the tangent bundle, I can think of a subsheaf of the cotangent bundle. Okay, of course, it's gone. But of course, if TF embeds in TX, then the dual of this embeds inside the cotangent bundle. Okay? And now I can take the qth form, right? So I can take the qth wedge here. This is a rank Q sheaf. So if I take the qth wedge, I'm going to get sheaf of rank 1 inside omega q of x. So this is defined by a section. A local section. And what are the properties of this local section? Of course, which follow from these two properties, mostly one. So first of all, omega, it's always decomposable. So maybe let me continue here, such that the first property is that locally, everything is analytic. Omega is to the form omega 1, wedge omega 2, so on all the way to omega q. The second property is that if we take d omega I, wedge omega, this is always 0 for I. Okay? And the opposite is also true. You can define a foliation locally around the point by a form omega, a Q form omega, which satisfies these two properties. Now, in these lectures, I will talk a lot about Q equal to 1, corank 1. So corank 1 it just means that you define by one form, omega, such that, well, this is, of course, the first property is not very interesting. Sorry, I should have said these are one forms. The first property is not very interesting, but the second property is interesting. So, such that the omega, wedge omega is equal to 0. Okay? Again, I won't need this, so that's why I mention it now. Okay. So let me give a few definitions, although they are very, pretty much all the same definition. So a subvariety W is tangent to X, is tangent to F, sorry. If, so there are many ways to define this, but let me just say that, let me just ask that if the tangent space of W inside the X factors through Tf is equal to W. Sorry, this one. Okay, so what does it mean? I mean, it looks fancy, but it's, what it really means is that if you take all the tangent direction to W, this, you can think of them to be element inside here, at the general point of W, outside the singular locus, of course. Then a definition we'll use all the time is something similar, but it's a bit confusing. So let me just do it for Q equal to 1, although it's the same for any rank. A divisor D is called invariant or F invariant a divisor means upper surface, sorry, upper surface. If, so we have a factorization which is pretty much the opposite of what is written there. Sorry, T, you have this kind of stuff. If you can find the factorization this way. Okay, how should we think of this? Well, at the general point, D is nothing but a leaf. Okay, so what is going on? If Q is equal to 1, this is just C, right? So these are all hypersurfaces. So a divisor is called F invariant if at the general point of this divisor, it corresponds to one leaf. So locally, D coincides with a leaf. Of F. Okay? Okay, and there's one more word, but again, sorry, we use these words all the time, and I don't know who came out with all these words, but they're all very similar, tangent, invariant, and so on. But so given a germ around P, and let's suppose that P is a singular point of F. Then a upper surface S of X passing through P is called separatrix. If it's invariant, if it's F invariant. Now you need to be a little bit careful here because we're assuming that it passes through a singular point of f. So let me draw a picture. Let's see what can happen. I should say also that we have this definition even in the formal neighborhood, and we'll use this in the third lecture. But, yeah. So given a germ around a point P, which is contained in the single locus of f, a hypersurface S of x at the point P, maybe P is not a very good choice because P is the rank, okay. It's called separatrix, this definition separatrix, if it's F invariant. So in other words, if it satisfies this property. The difference is that I'm forcing S to pass through the singular locus. So let me draw a picture of what things can look like. So you have a single point, and then you have all the possible leaves. But through the single points, you can have more than one, okay. You can have something like this. Okay? So the reason why there is more than one leaf passing through one point is because this is a singular point. So these are not called leaves, but they're called separatrices. Okay, and we will study this in details even in a few minutes. But let me give an example. An example which is always good to keep in mind. Let's suppose that X is a smooth surface which maps to a smooth curve. Let's call F the proper map. Okay, so as I mentioned before, it would be very tempting to take the kernel of the induced tangent map but this in general is not saturated. Why? Because there could be multiple fibers. Okay? So TF is the saturation, sorry, I don't have space. It's the saturation of this inside Tx, of course. Okay, you have this, you take the saturation and you get a subsheaf. And this is easy to check that it's, it's rank one foliation. So it's very easy to check. There is nothing to check pretty much. Of course it's saturated by definition, and also closed under the bracket, it's obvious because it's rank one. Okay, so TF defines a foliation. Now, you can do the calculation, and you get that Kf is equal to, it will be very tempting to stop here. Sorry. One could say this is the tangent, the cotangent sheaf. Which would be true if if this is already saturated. If you do the calculation, then, by this I mean Kx minus F star of Kc. It would be very tempting to say this is true because it would be very tempting to say that this is true. But unfortunately, this is not always true, so you need to add an error. So the error is given by the multiple fibers. So what is this symbol? D, it's a vertical curve. What does it mean it's a vertical curve? It means that it's mapped to a point here. And what is LD? So such that if we take the pullback of f of d it's a point, right? Okay. This would be the sum of some curves, including the V, of course. Okay, and this is the ramification, it's the multiplicity of di along the fiber. So this is exactly what this LD is. Okay, you can do the calculation, and you can see that you get this formula. Okay, so you see that the goal of the MMP is that instead of studying Kx, you study this kind of divisors, which didn't appear very much in literature, as far as I know. Okay, let me skip this. Okay, let me start talking about Baratian geometry now. Okay, so I had to make a choice. How do I present this if I didn't explain the program? So what I'm going to do is to try to run the history, well, not the history, but some of the necessary steps in Baratian geometry. If you want to learn Baratian geometry, the first thing that you need to do is to learn about resolutions. I mean, at least know what a resolution is. Okay, so I'm going to do it for foliations, but I'm going to try to mimic exactly the same for proper varieties. So let me start by saying that given a Baratian morphism, we can define, there exists, and given foliation on X. I already mentioned it, but without any comment. We can always induce, there exists F prime, foliation, induced on Y. Induced, sorry. How do we do that? Well, you know that these two objects are isomorphic outside some properties, some subvarieties. Actually, you know even more, that you can remove something of a dimension greater or equal than 2 here. Okay? So you can take the pullback of the sheaf and then extend it and take the saturation. This will give a foliation on Y. It's easy to check this. It's a natural foliation on Y. Okay? So what do we do in Baratian geometry? We know that by Hironaka, so Hironaka famous theorem says that if X is a normal variety, of course if it's not, you can just take a normalization. There exists P from Y to X proper birational. Such that Y is smooth. Okay, so can we do the same with foliations? Sorry, I forgot to say something, but okay, let me go back in 1 minute. So can we do the same with foliation? Well, the answer is not. And the example is extremely simple. But I should have said before why. So let me go back, it's exactly the same example as before. So let's suppose that f from x to c is the fibration as before. And let's suppose that f is the induced foliation. then it's a very easy calculation, and I should have said before, that the singular locus of F is the union of all the singular points of all the fibers of F. So let's say union of singular of F, where F is a fiber. So what does it mean? It means that suppose that this is the fibration, then these 2 points are the singular point of the foliation. Okay? Now, let's suppose that we can resolve singularities like in Hironaka's theorem. Then it means that if you blow up, at some point you get something smooth. But actually, if you think about that, you're going to get something even more singular if you blow up. Okay, suppose that you have something like this. You blow up this point, you're not going to get anything which is smooth. You're going to get, I don't know, something like this, I suppose. And you can continue to blow up. You're not going to solve anything. You're going to create even more singularities, right? You increase the number of singularities. So there exists no resolution. Even if you take the most simple, this is for sure the simplest foliation. Even in this case, there is no resolution. Okay, but we cannot work, you see, we cannot work with smooth foliations, because smooth foliation corresponds to smooth fibration, and smooth fibration are very, very, very rare. So from a Baratian geometry point of view, for sure, they don't have any interest whatsoever. Okay, so we have to do something like that, something different. And here we talk about, I'm going to talk about McQuillan point of view, although there are many, many people involved. But I think McQuillan is the first one that noticed that all this behaves very much like Baratian geometry. Okay, so maybe many of you know what a canonical singularity is. So let me recall you. X is called canonical if, so I'm talking about no foliation, I'm really talking about varieties. For any P from Y to X, proper birational, let me just say birational. We can write, so you see, we can define ky, and we can define kx. Oops, sorry, I always forget to say. If, first of all, is Q-Gorenstein. What does it mean, Q-Gorenstein? It means that even if kx is not Cartier, is not defined by invertible sheaf, it still makes sense to talk about kx as a Cartier divisor. So in other words, there exists M positive such that MKX is Cartier. Okay, and so these are the two properties. For any P Baratian morphism, you want to compare, now it makes sense to talk about pullback of kx. And we want to check what is the difference. So usually these two are not the same, there is an error. And the error lives inside the exception divisors. Sorry, let me just say E, where E, it's an effect divisor. And of course it's P exceptional. Okay, maybe if you've never seen this before, it doesn't help too much. But what it means is that if you have a form of maximum order, a n form on X, you take the put back, then this basically you can write in this way in such a way that the order, you only have vanish along E. Okay? So somehow these are the singularities that seem to be the best well behaved in the mu model problem. So for foliation we can do exactly the same. So let's assume now that F is a foliation on X. Okay? I'm not even assuming possibly singular. I'm not even assuming that X is smooth. And the definition of foliation is exactly the same as I gave a few minutes ago. Then F has canonical singularities, this definition. If, exactly like before, Kf is Q Cartier, which one more time means that one multiple of Kf is Cartier. And for any P like before, we can write Kf prime equal to P star of Kf plus E, where this is the induced foliation, and E, as usual, it's P exceptional and disaffected. Okay, so it's exactly the same definition. Now, of course, your question could be, why is this a good definition? Why do we care about this kind of definition? I will give hopefully many more reasons why we believe this is the right definition, but let me give a very basic definition, a very basic reason, sorry. Okay, sorry. First of all, even more basic, sorry. A fact, which is not completely obvious, but is not difficult to check, is that if X is a smooth point, then F is canonical around P, and around X. What does it mean? This is a local property. You can take a neighborhood around the point and check if this property holds. So if you take a smooth point, then it's canonical. Except in the same way, if you have a smooth variety, then it's canonical. Of course, this is not a good evidence that canonical singularities are good, because I could have chosen smooth foliation. So let me give a better reason. Let me go back to the example we studied a few times. Let's suppose that F, as usual, is a map from a surface to a curve, and let's suppose that F is the induced foliation, and so on. Then one thing that you can check by hands is that F has canonical singularity, or is canonical, if and only if the fibers are simple normal crossing. So locally, they are nodes. They are made of two curves, or one, which are both smooth and then meeting transversally. Okay? So, you see, This is good. We like, although I told you, there are not many fibration with smooth fibers, but there are a lot of fibration with fibers which are simple normal crossing. So we're not losing much. We're not losing many fibration. And actually, even better than that, if you blow up, you can always suppose that this is true. So given X to C, there exists always a sequence of blow up such that from Y to C has only simple normal crossing fibers. Let me draw a big picture. I'm not going to prove it, but let me draw a picture. Although the proof is obvious. You suppose you have a cusp, then after you blow up, I suppose you get something like this, and then you blow up one more time, and I'm sure I'm going to do a mistake, but anyway, you're going to get something like, what do I get? Something like this. And then you blow up one more time, and you're going to get the fibration with simple normal crossing singularities. Sorry, I think that you already saw this before, so I'm not going to spend too much time. Sorry. So you need 3 blow-ups. But after 3 blow-ups, if I didn't do any miscalculation, you get a fiber which looks like this. It's not a reduced fiber in general. Sorry, maybe fibers are the reduction, the reduced fibers, the reduction, sorry, of every fiber are simple normal crossing. In other words, I'm not assuming the fibers are reduced. I'm just assuming that the reduction is simple normal crossing. Okay, so we can always blow up until you get a foliation with canonical singularity. So now I can ask you the same question as before. Given a foliation, can I resolve the singularity partially? This is a nice question. And I think it's due to McQuillan. This is a resolution singularities. It's the right question. At the beginning, they ask the right question. We don't want to make it smooth. But given given f on x, does there exist p from y to x, birational, such that f prime, where f prime as usual is the induced foliation on y, has canonical singularities? Well, we don't know yet, but we know it in many cases. So for n equal to 2, for surfaces, this is a very old theorem due to, and also, although of course it was using a very different language, but it's due to Siedenberg. For n equal to 3 and rank 1, sorry, let me do rank 2 first. This is due to Kano. And I will talk about this a lot. For n equal to 3 and p equal to 1, this is due to McQuillan and Panazzolo. But you need to be careful because in this case, p is not a blow-up of smooth points. So even if x is smooth, you might be forced to take weighted blow-ups. In other words, you have a price to pay. You make f canonical, but y could become singular. But it's okay. Any questions so far? Okay. So let me give one more definition, which I will always use. So F is called non-decritical if for any, as usual, pi from y to x, and yeah, decritical. And for any q point of x, sorry, we have that. So let me write first, and it's very easy, but let me write and then I will try to justify why this is important. Wow, I'm using very bad. Oh, let me say x, sorry. For p minus 1 of x is tangent to f prime, where as usual f prime is the foliation induced on y. Okay, let me say why this is important. Because let's consider the case of a surface. So let's assume that X is a surface. And let's suppose that this property is non-true. Let's suppose that P is a blow-up, such that the exceptional divisor E is not tangent. Okay? So what is the picture? Well, you have something like E on the surface Y. But this E is not contained in the singular locus, because we say the singular locus is always codimension 2 or bigger than 2. So it means that through the general point of E, there must be a leaf. Okay, which cannot be equal to E. Why? Because E is not tangent. Okay, now when we contract E to a point, all these leaves will be still leaves. So what we have is that we have infinitely many leaves through a point. So this very, very simple explanation shows that if you have something which is not non-decritical, then you always have infinitely many leaves passing through a point, which is bad for what we're planning to do. Okay? So there are infinitely many leaves through the point X. Okay? We will see that this is something we want to avoid. So actually, let me tell you a spoiler. We don't know if canonical singularities are non-decritical. By using the minimum of the program, and I'm going to talk about this in the third lecture, we can show that in dimension 3, of course in dimension 2, it's by Seidenberg. I mean, this is just easy. In dimension 2 or 3, canonical implies non-decritical. This is due to myself and Spicer. But the way we prove this is to use the minimum of the program. So although it's not needed, I will always assume that F is non-decritical and canonical, because that's how we prove theorems. And then at the very end, we're able to prove this. It's a bit strange somehow, but it works. Okay, maybe let me give an example. I still have quite a few to talk about, but let me give an example. Let's work on C2. And let's consider one form omega given by y dx minus lambda x dx, x dy, sorry. So this defines, so where lambda is a complex number which is non-zero. Sorry. This defines foliation. And now, this foliation is canonical if and only if it's non-dicritical. So f is canonical if and only if lambda is not a rational number. Okay, what is the picture? The picture is that if lambda is a rational number, positive, then you have exactly what is written there. All the lines to the origin are leaves. These are all the leaves. So it cannot be canonical, it cannot be non-dicritical. On the other hand, if the opposite is true, then you have a picture which is similar to what we drew before. You still have two leaves passing to the origin. The origin is a singular point. So there is nothing to be surprised about if there are two leaves. But then all the others will be just like this. Although it's difficult to picture, but somehow it will be something like this. Depends on lambda, but something like this. Okay. So the next thing that I would like to talk about it's log pairs. So when we work with the minimum of the program, we don't initially work with x, but we work with, we replace x by some pair, x delta. What is delta? Delta, it's a linear combination of hypersurfaces. So the reason we do that is because kx is not very well behaved from any point of view, like a junction does not behave well with respect of kx and so on, or the canonical bundle formula. So we replace kx by kx plus delta. Okay? And many properties of kx are true for kx plus delta if x delta satisfies some properties, which we assume. First of all, we will always assume that the ai are within 0, 1, maybe 1 included. We need more than this. But many properties that are true for kx are usually true also for kx plus delta. And kx plus delta is much better behaved than kx because it's closed under a junction and the canonical bundle formula and many other things. Okay, so for foliation we do the same. Instead of working with f, we work with f delta, where again delta is equal to ai psi, and ai are rational numbers which are within 0, 1. And instead of working with kf, very often we work with kf plus delta. Okay, because again, this is much better behaved from many points of view. Okay, so in the next 5 minutes, let me give the definition of KLT, and then I'll start from there tomorrow. So KLT is very similar to canonical for a variety X. So let me just define it. Well, let me remind you the definition. Sorry, maybe I should do. So x delta is KLT if, first of all, kx plus delta is Q constant, sorry, is Q Cartier. And one more time, for any p from y to x, the pullback of kx plus delta is equal to ky plus delta y, and I'm going to explain, okay, maybe now, delta y is nothing but the strict transform of delta. Plus something exceptional. And now, I don't want to lose the category. I don't want to be in a different category. So what we need to assume is that, such that, I forgot to say something, sorry. If the coefficient of delta, so the AI are within 0, 1, where 1 is not included. So this is the first property. The second property is this one, and the third property is this one. So, but let me write the AI must be less than 1. Again, because otherwise I go out from the category. If this was too big, then we'll be in trouble. We lose the fact that we work with these kind of pairs. I will try to justify later on why this is a good definition. But let me give a remark. AI can be negative. So this is possibly negative. Okay, for foliation, this is very similar, but we need to be a little bit more careful. I cannot just copy the definition. Okay, so first of all, given a divisor S, given F foliation, and S divisor, hypersurface, sorry, then we define, this is very stupid, but it's going to be very useful and I'm going to use it all the time. So I will try to remind you whenever I use it, but epsilon S, it's equal to 0 if S is invariant, and 1 if S is not. Okay, I will explain in 1 minute why this is good, but let me give the definition first. So, F delta is KLT if, first of all, the coefficient of delta are less than 1. Okay, let's see. The second property is that Kf plus delta is Q Cartier. And the third property is exactly like before. If let me write it the same way, P star for any P from Y to X, P star of Kf plus delta is equal to Kf prime, where F prime is the induced foliation, plus delta Y, where delta Y is the strict transform of delta, plus the error, which is given by exception divisor, where, and here you need to be careful, I'm not assuming that AI are less than 1. But I'm going to assume that AI are less than epsilon of EI. So what does it mean? It means that if it's invariant, if it's not invariant, then it's exactly before. It's less than 1. If it is invariant, then you want it to be less than 0. It must be negative. Okay, I just take 2 more minutes to explain why this makes sense. So first of all, KLT is good because if you start from something KLT and you do minimum of the program, you continue to be in the KLT setup. So the same story holds for foliation. But why do we have something strange like this one here? So maybe you wondered, why do we have this stuff less or equal than 1 or something like that? The reason why we like very much 1 or something less than 1 is because, I'm going to talk about this next time, of adjunction. You remember very well that if you have kx plus s plus something delta, like delta, let me be very naive, and you restrict to s, this is not equal to, this is equal to ks plus some theta, where theta is greater than 0. Okay? If everything is smooth, then the theta is nothing but delta restricted to s. But the idea is that you need this s in order for things to be well behaved. Well, for foliation, we will see that the formula is slightly different. It's not true that this holds. I'm going to be very sketchy here. For foliation, we like to have such a formula, right? Because we're trying to imitate the minimum of the program. But written this way, it's wrong. The correct formula is this. In other words, if S is not invariant, then the formula is exactly the same. So here, let me write just for some G. If F is invariant, then this is exactly the same. If S is invariant, then you just eliminate this term from this formula in order for this to be true. Okay, we're going to see this tomorrow better. But this is why we need to be more careful in the definition of KLT singularities in this particular case. Okay, thanks for your time.